In part 2 of our series on reviewing the acid naming system, we're going to look at a different type of acids from the typical binary acids, which are what we call the oxyacids. And not surprisingly from the name, we can see that oxygen is by far the most common element that occurs within the structure of the acid, although all of the oxygen is actually found inside of a polyatomic ion, which makes the name a little bit misleading. So the actual proper name that would hint on where these acids come from should probably have been polyatomic ion acids instead. So for example, we can see here in this top oxyacid that the polyatomic ion is nitrate. So we can see that the polyatomic ion could end in ATE as in nitrate, but we can see this acid based on a polyatomic ion is based on the polyatomic ion nitrite, which ends in ITE, and this distinction, whether it's an 8 polyatomic ion or an ite polyatomic ion, is the critical difference when it comes to naming oxyacids. In fact, this is the first step. So if we identify that NO3- goes by the name nitrate and NO2- goes by the name nitrite, this is the main distinction that we need to establish. So in the same way that the non-metal in a binary acid, so Cl in HCl, forms the root of the acid name, it is the polyatomic ion that does so here. So nitrate is going to be the root of HNO3 and nitrite is going to be the root of HNO2. So now comes the time to remove the suffix from each of our polyatomic ions, which would mean that each of these acids is temporarily going to look the same in terms of its name, but we see if the ion name ends in ATE, we can replace this with the same suffix that we saw with binary acids, the suffix ic acid. So the polyatomic ion nitrate, if we were to add a hydrogen to it, you would be making nitric acid, as long as this acid, of course, is dissolved in water, whereas the polyatomic ion nitrite, if we were to add a hydrogen to this, we would add the suffix OUS acid instead, which would be pronounced nitrous acid. So this is why we often say that ite becomes an us acid, whereas ate becomes an ic acid instead. Now, the only exceptions that we need to go over here are not so much exceptions to the rules, but are exceptions in terms of English spelling, because as we know, English is probably the most frustrating language to learn in terms of the number of irregularities that exist within the spelling system. And for that, we need to turn to these two example acids here, because they are oxyacids that contain either the central atom sulfur or the central atom phosphorus, and both of these names are actually going to give us a little bit of a hint as to the slight variation in terms of how to name them. So the first step when naming any oxyacid with sulfur or phosphorus as the central atom is actually to name each of the elements, sulfur and phosphorus, because those are the names to which all of the changes are going to apply. So in this first acid here, we can see that the polyatomic ion is SO4 2-. So in this case, this polyatomic ion would be sulfate. So because this polyatomic ion ends in ATE, just like nitrate or carbonate, for example, we can directly onto sulfur add the suffix ic acid. So rather than being called sulfic acid by removing the UR prefix, we actually start with sulfur as the root of this acid here, and then add ic acid directly to it like this. So this would be pronounced sulfuric acid or sulfuric acid, and we can see the spelling distinction is minor, but it is there nonetheless. And likewise, the polyatomic ion SO3 2- that we see here goes by the name sulfite. So if our polyatomic ion ends in ITE, we replace, or we don't replace anything, but add the suffix OUS acid onto it, so this acid would not be sulfus acid, as I very nearly wrote here, but would be sulfurous or sulfurous acid, as the name sulfur takes the root of the name that we write here. Now, of course, if this were the rule for phosphorus as the central atom in an acid, everything would go easily, but of course, English is not that simple. So first off, we can identify what the polyatomic ion is in the acid. In this case, this would be PO4 3-, which is going to be the polyatomic ion phosphate, and then over here we have the polyatomic ion PO3 3-, which goes by the name phosphite instead. And again, we can see ATE replaced with ic acid, ITE replaced with us acid. But in this case, we start, just like with sulfur, with the element name and not the polyatomic ion as our root. So we start with phosphorus, and in this case, we're going to remove the suffix us so that we have phosphor as our root for both of these acids here. And if the polyatomic ion ends in ATE, as it does with phosphate, we replace it with the suffix ic acid, so this acid name would be pronounced phosphoric acid, whereas if the polyatomic ion ends in ITE, we replace with OUS acid, and therefore this acid would be pronounced phosphorus acid. So again, the rules don't really change. ATE polyatomic ion still becomes an ic acid, whereas ITE in the polyatomic ion still becomes an us acid or an OUS acid, but the slight spelling irregularities necessitate this little detour here. Before we move on to looking at how oxyacids are actually produced, you can take a look below at the practice problems here and see how many of these oxyacids you can name now that you have the naming rules, before taking a look at the next video, which looks at a pattern in the naming between many structurally related polyatomic ions and looks at a few strategies in terms of identifying a pattern that will make it easier to name different closely related oxyacids.